Okay, so we've talked about mixers now, how it looks like, and this is actually what you'll be doing at ZSpice. I'll release the assignment later today. Luckily for you, it's not that hard. Correct trick is like I have like design interviews. I give you the diode models. These are really tricky to make, but you can just like, I'll send you like a link for it. It takes like 10 seconds. And after that, all it is you put the signal here, you put a signal here, and you look at the output and it's like, oh, the frequency domain, what does it look like? Is it mixing? Great. That's it. So pretty quick compared to previous ones. And the main reason I would like you to do the assignment is because for the work session, not the upcoming one this Sunday, but ideally next weekend, we'll be making mixers.
So are what is the values for the, the inductors going to be like just given to us, or?
Yeah, I'll give you all
So
of
it's
that.
not like we like figure out like
No.
we switch values around and
No,
see
I'll
what
give
it
you,
does.
because the values don't matter, right? We care about the turn ratios, whether
Yeah.
that's just 1-to-1. Obviously, we want the values to be some reasonable value, nonetheless, but something that we can make with what cores we have, but values doesn't matter.
Yeah. Are you like in theory, right? We have the dot for couple.
Sure.
Like, how do you like do that in practicality? Like, if we line our own inductors,
Sure.
how do you do that?
We'll end up what's gonna happen is like, you'll grab, this is like a side view. You're gonna have two different colors here, which is perfect. Shit, how do you do perspective? Just assume one goes like this or something. It just goes around, okay?
Yeah.
And it's gonna find its way all the way like this. So that's one like inductor, right?
Yeah.
And then the other one we just wrap around.
Oh, with it.
And depending on which way the dots are, like they're the same, so we'd wrap it around the same way. I guess I should have started over here, but you get the point.
Yeah.
Often you wind it the other way. That's kind of how you do it. Yeah. It's a bit tedious, but like, yeah, it's kind of fun. I think this is the only time. This is the only time I'm gonna use this. We use inductors quite a bit in rap for mixers, for our amplifiers, for filters. Filters you'll be using your own hand-wound ones, but I think for the mixers I'm going to use SMD ones that are already in the package, just for better performance. Because the whole point of the inductor is to make it balun anyway. May as well just use an external balun. Right, it's a bit better for performance. So there's that. Okay, so now we're just going to quickly talk about what we care about in a mixer, and what you should be looking out for on your assignment. It's not that complicated, like in the sense where you don't have to use exact parameters a mixer mixes. For rap, we don't care how well. I mean, obviously we do, but not all the nitty-gritty details. But for future reference, it's important to understand some idealities of the mixer. So first thing is some of our LO is going to leak. Ideally, at our output, we don't see any of the LO. We just see the RF plus IF, RF minus IF. The difference between the LO and the IF frequencies, right? But sometimes we will see the LO go through as well, and we in fact do all the time. And it's a fairly big problem because LO is going to be very close in frequency to everything else, so it's harder to filter out. That's just one little detail there. So I used the word balanced earlier to describe this mixer. Okay. There's something called an unbalanced mixer, and I'll kind of show you what it would look like and how that compares to this balanced mixer. So, in an unbalanced mixer, we have no isolation. So in the case of down conversion, some of our LO signal, and this would be reverse for down conversion, RF here, IF here, some of our LO signal and our RF signal would leak into our IF. Okay? So it kind of seems like leakage is a big issue here, right?
Is that only for down conversion?
But in up conversion, right, you can have your LO and IF leak into your
Yeah.
RF, right? So it's for down conversion, LO and RF, vice versa for up conversion. So that's kind of annoying, okay? The reason being is, you know, let's say your RF for down conversion, right? You're gonna go from 27 down some intermediate frequency down to 1 megahertz. If you have some of your 27 leak through, maybe something down the line is not meant for 27 megahertz. That's gonna get in the way and disrupt its behavior. So we wanna minimize that, generally speaking. And here we have this notion of unbalanced. Here we have our LO and we have our IF. So this is down conversion again, and we can see that our IF only has a signal when our LO is positive. This is unbalanced. Whereas over here, we had two cases, positive and negative, right? So we had some output when even when our LO was positive or negative. That's why this is balanced. In other words, it most effectively uses your LO. It doesn't waste your LO signal. And when you care about power consumption, that's very useful to use a balanced one. And there's also some differences in performance, what frequency range, etc. that comes with that, but generally speaking, balanced is better. And what does this look like? Well, some of you who did 115A may kind of recognize this circuit. Right? Right, it's a diode circuit connected to some network. When it's positive, right, this voltage will turn on, you'll see a signal. It's negative, no signal. So generally speaking, whenever you have a diode or any switching that chops up your signal, you're gonna have some, I don't want to use the word modulation, but I'll use the word modulation of your signal, and that typically refers to some changing in frequency that's I wouldn't say it's like doubling necessarily, but you are adding or decreasing by some amount, which could be the same. It could double. Generally speaking, the frequency would change. And that is pretty much it. There's one more thing I would like to mention here, but a single balanced mixer. And this is not something we're going to touch on at all in wrap, but just to give you some insight into what's happening. This is another type of mixer you have. Looks kind of weird, but the idea is you have something that will sum up your A and B inputs if your LO into the difference, and output to get your IF. This can only remove either the LO or the RF from your input, but not both. And this is pretty, it's like a block diagram, really. It's not specific like topology. You can use different ways of implementing the structure. This is something that I've not used. I've used mixers like diagram mixers. I've used rad race mixers, which is like a microwave structure, and I've used stuff for IC stuff. Not seen this used yet, but it's something that you can just kind of see. I think at the core level, it looks very different than that. Right? So, double balanced mixers like this one, there's a few good things about it.
Can you repeat the name of the one on the right again?
Yeah, that's a single balanced mixer.
Is that like a good pro to that one, as opposed to?
I would say it probably needs smaller LO power, and it's less sensitive to component variations. It's probably going to be used more at a microwave level than discrete. double balanced mixer, which is our diode ring mixer, tend to need a larger LO. We have to turn our diodes on in both directions, right? So we need a larger swing. It has good isolation, whether you're doing up conversion or down conversion, in this case down conversion, good isolation. It is sensitive to component variation. You know, if your diodes are unequal, stuff like that, your turn ratios are off. That's also a bit of a factor. So it's fairly sensitive. And lastly, you're gonna have some terminology, and we're gonna wrap this all up with filters, okay? Okay.
This single balance mixer, could you just
Yeah.
explain what you mean by larger LNO, like triplets?
Um,
Like
single
larger
balance.
frequencies?
Oh, yeah, it's, these different topologies, operate better at certain frequencies. Like if you're low frequency, diode ring mixer probably works, right? If you go higher frequency, well, your diodes just switch faster. At some point, you gotta go into microwave structures or stuff like that.
Okay.
Yeah. Basically just different topology that just happens to work better for certain things and not others. That's all. Okay, so this is one thing, conversion loss. All of you read that? Hopefully. Basically, it's the ratio of your IF power to your RF power. So this is for down conversion. For up conversion, you'll have the ratio of RF power to your IF power, right? Kind of makes sense. How much do you convert? Can be positive or negative. Ideally, you want it to be positive. Okay. Makes any sense. It's negative, it's not the end of the world, but you know, better if it's positive. Then we have LO isolation. And this is fairly self-explanatory. Okay, it's the amount of power that leaks into your output. So if you're doing down conversion, your output's your IF, up conversion RF. Negative 40 dB is good for this. So in your assignment, you'll be able to look at the FFT and be like, okay, look at my LO frequency. It's negative 40 down. Okay, good. Pretty quick, pretty quick check. Next, there's RF isolation. And this is for down conversion here. And kind of straightforward, how much of your RF leaks into your IF? That's the ratio. Next is LO drive level. Kind of briefly touched on this for the whole diode thing. You need enough power to turn them on, right? And you can describe this as the amount of LO needed for the proper function of the mixer. Okay. Many diode ring mixers are going to require +7 dBm. So they need around 7 dBm, which if you go from this power from dBm to milliwatts to assuming a 50 ohm termination, if you want, I can go to the math later, but you can look at the formulas as well. This corresponds to a roughly 0.7 volt amplitude, right? Kind of crazy. 0.7, have to turn your diodes on, and 0.7 is also what the VBE of BJT. Kind of crazy. So that's something to remember. That 0.7, 7 dBm, kind of lines up. Lastly, is something called noise figure, which is okay, it's something I've spent 3 weeks on learning in 215C. So I'll briefly describe it here because it's very complicated. But it's this idea that, so you have down conversion, you have some antenna, you receive your RF signal, give me some noise with it. And your RF signal is not going to be very strong, you just transmit it over like some distance, right? So it's going to be pretty weak. So whatever noise is there is going to be pretty strong relative to it. Call it that like the signal to noise ratio, right? That's how you can characterize that difference. So you have a certain signal to noise ratio, and draw this out. You have a certain noise ratio, you have signal to noise ratio. And ideally, you do not want that to get worse as you modify your signal, as you do things as a down convert. In fact, you want it to get stronger. You want your signal to pop out more from the noise. You want it to stand out more. This is not something you're going to worry about in your assignment, but generally speaking, as you do, if you decide to pursue RF design and any IC design, noise figure is very useful because it allows you to kind of characterize how much different stages affect the noise performance of your system and overall how you can design around that and minimum requirements, stuff like that. Yeah.
What's the main difference between the noise figure and like your SNR?
So yeah, good question. So the best way to your SNR effectively is, let's start describing this. I don't go into too much detail. Your noise figure is your SNR in or your SNR out. It's a bit of a weird notation. You'd expect it to be out over in, but it's the other way around. This can be expressed in terms of linear or dB, and this is just the correlation there. Your signal to noise ratio is like your signal level and your noise. Yeah. You'll see that even if you have like a very good low noise amplifier at the input of a receiver, you're always going to have maybe 2 dB, 3 dB. Ideally, you want it to be as close to 0 dB noise figure, but you're always going to have at least 1 dB noise figure, so you'll always have some degradation there. The question is now if you have gain and stuff that factors into it, but this is something you worry about later on. The main things for this assignment is this, which you've met already because I'll give you the right values. LO isolation, you'll check. Same with RF isolation, you'll just do it, an FFT, right click, plot DFT, you look at those 2 values. And that's good. So that's everything on mixers. Times it. If I have like 10 minutes.
616.
Oh, okay, that's good. Yeah. I'm going to cover filters super briefly. You've all seen filters to some extent or no?
Use a Bruno all the time, dude.
Yeah, the 141. Yeah. I'm quite sure we all get PTSD.
Before you get into that,
Yeah.
like, now that we've gone through everything for like the module or whatever, what are we actually doing on our end? Like,
For the rap board or just the
or like for the extent of at least this lecture, like
Yeah.
it seems like we want to check like leakage of IF and RF,
Yeah.
vice versa,
Yeah.
whatever. But like on our end, what are we changing to change that if everything's doing?
Oh, I see. Okay. So what's going to happen is the assignment is going to be like, okay, go from this frequency to that frequency. Okay. And you don't just go from 1 to 27 megahertz. I'll get into that like right now. Okay. But the idea is, we go from 1 to some other frequency. Some other frequency is 27. Make a mixture that does that. At which point we use the same topology there, and verify, hey, this topology, kind of values given, is your LO leakage less than blah blah.
Okay.
That's it.
So it's like topology is kind of like the design constraint for this.
Yeah, exactly. that's something I want to talk about. So, some of you may ask, why can't we just go from 1 megahertz to 27 megahertz or vice versa? Kind of a reasonable question, right? Why we want to do it in 2 stages, take some more components, et cetera, et cetera. It's kind of weird. So, we go from 1 to 27, okay? Let's look at the frequency spectrum here. Okay, we have our IF of 1 megahertz. Okay, and to go to 27 megahertz, can anyone tell me what the LO signal should be? Let's say, take a guess, any guess.
Like, I'm trying to like think like a fundamental harmonic.
Sure.
26 megahertz.
Sure, yeah, 26, right? Okay, so that's our constraints, right? We want to go from 1 to 27 megahertz. Hey, we're kind of stuck at our IF being 1 megahertz. Our LO is stuck to being 26 megahertz, right? If we go over here, we're going to see 26 some LO leakage. We're going to see our, our 27, which is what we expect. And then we're also going to have, maybe some 25 component, right? Some difference. And of course, we're going to have some harmonics and stuff, right? We're going to have, these are terms I'm not mentioned yet. We're going to have stuff like intermixing. We're going to have spurs, more leakage. I can backtrack and intermix. A bunch of other things that can happen, which means this is going to be a lot noisier than you think it is. When I use the term noisier, I don't mean physical random noise. I mean noise as far as you're going to have other frequencies pop up that are a result of our mixer that are very close to our frequency range of 27. So maybe, this is fine, right? We can just apply a filter. These are very close together. If you want to filter 27 from like 50 megahertz, that's a bit easier. Very hard to have a kind of a filter that looks like this. Very hard to do. So that's why we can't just go in 1 stage. There's another reason, and this has to do with the architecture of our mixer, and going back to the idea of what's stopping us from just going, we have RF of 27 megahertz, why can't we just down convert to DC? Why can't we LO be 27 megahertz? In fact, that's what's done a lot of times nowadays in RF design. It's called direct conversion, and it solves a lot of the problems that heterodyne receivers have, which is a really different topic. But basically, doing it in 1 step is bad for this reason, right? And the general idea is, yeah.
So you want to like cascade your mixers?
Exactly.
Okay.
So what we instead decide to do is we're like, okay, we have 1 and 27, starting and end. We want to go there in 2 steps, and we want these steps to be equal, right? So, I don't know, let's say 27 is close enough to 25. And square root of 25 is 5 megahertz. So 1 to 5, 5 to 27. It's good enough. That's a general idea. If you had 3 stages, you'll do like the cube root and go in increments like that. And that solves a lot of the problems. I wouldn't say solves a lot, but it helps you remove these other frequencies from being as tight of a filter, okay? So in reality, in RAP, we can go from 1 to 5 to 27, is the idea, and vice versa, going down, okay? So for that, we need 2 mixing stages, and of course, after every mixer, we need a filter, right? So there's that. Any questions on that? Cool. As for filters, there's a whole class on filters that Jarabi sometimes teaches. Very useful class. I'm gonna try and convey some of the properties of that here, and hopefully it'll give you a good understanding of what a filter does. Okay. All of you have seen a filter before, right? You know, a filter isolates frequencies. You know, you can't really have gain out of it. If it's a passive filter, rather, you can't have gain. If it's an active filter, yes. Okay. So for a passive filter, you all have seen maybe an LC circuit, right? A resonator, or rather an RLC circuit. It's gonna have some kind of band pass response, all right? So something like this, and we're gonna see it has a frequency domain. This is omega naught. Kind of what its response will look like, where omega naught is right? And if we do the Bode plot perspective to this, you'll see that it goes down negative 40 dB per decade on each side, past a certain point past here. Okay. Now let's say we have some normal, high pass filter, let's say, for example, or let's do let's do high pass. Yeah, let's say we're going to transmit to an upconvert, but a high pass filter, right? So we all kind of know what that looks like. It's gonna look like this. Right? Take this out, this voltage, high pass filter. If you look at the Bode plot, we're gonna start off at some amount, we're gonna go down 20 dB per decade, and it's your negative 3 dB mark. And if you look at the phase, it's gonna start off here at the negative 3, we're gonna end up at negative 45. That's gonna look something like this. Right? Just, general kind of circuit theory stuff here, right? So, okay, we know there's some high pass filters, some low pass filters, and some band pass filters. We're not gonna use band stop in rap, but 4 type of filters, right? The question is, what filters do we choose and why? And you'll see that in this next module, alongside the mixer one, at the very end, there's going to be a little tool you can use, like a website, and you'll put in certain parameters there, like what frequency of interest you have, et cetera, and it'll spit out a filter for you. But it's gonna be a lot of things that's like, okay, what is this, okay? There's a few things we do in filter design. First is, there's notion of a doubly terminated filter, and what that does is as follows. Let's say we have a second order filter here, band pass. Looks like this, okay? Let's say you design this band pass for, 27 megahertz, for example. Or rather, let's say we design it for 5 megahertz. We go from 1 to 5, right around 5, we want to cut out everything else, right? Well, what happens is these filters, in order for them to work as intended, for them to have the right, degradation of your of your frequencies outside your passband, they need to have a certain termination. They need to have these resistances be a certain value. And just like an RF design, we say, let's have these resistors be 50. Right? So if these resistors are 50, and this computer program will spit out whatever values we need here, when we have to solder it, we're like, okay, assuming the next stage that we have after the filter is 50 ohms, looks like 50 ohms, and the one before, which is our mixer, looks like 50 ohms, this will perform exactly how we expect it to. In reality, maybe it's not exactly 50 on both sides, it's not going to perform exactly like we need it to, but it'll still work. This is another reason why we want 50 ohm terminations, alongside just having everything be nice and 50 ohms. Thus, for conjugate matching and power transfer and reflections, also our filters work as intended. And you can probably expect, hey, this is a fairly tight response, right? Negative 40 dB per decade. But say we want an even tighter filter. What do? Well, we just put more inductors and more capacitors, right? Maybe you have something that looks like this. Right? This would be 5th order now. And you can have another inductor there, make it 3rd order, etc., right? So as you go higher and higher in order, use more elements, it's more costly, you get a tighter response. Maybe over here you'll have something that looks like this. Yeah, let's ignore that for now. It's really hard to draw that discrepancy, but basically, you can have a way steeper response for this, which we expect, right? Another thing is, that's very good, but in reality in RAP, we're going to stick to either 5th or 3rd, which would just be those 3. There's 2 types of filters that are also in the software, Chebyshev and Butterworth. And if you look at, this is not needed information, Chebyshev, if you look at your poles, it's going to be on an oval. And for Butterworth, if you look at your holes, it's gonna be on the unit circle. And the result of this is as follows. Butterworth, when you design your filter, it's assuming that in your passband, the frequencies you do not want to attenuate, you have a flat response. And after that, you want to attenuate the other frequencies. It's just gonna go down. But you have a flat response in your passband. This is your passband, and this is going to be your stopband. Yeah. For Trebuchet, the idea is in your passband, you'll have some ripple. You can go up and down a little bit, and then same drops off at the stopband. This ripple allows you to, what's it called, have more varied values and stuff like that. So it's not as tight of a filter. Both in the stopband have, whatever order there is times -20 dB, but maybe sometimes you care about the passband response you can get out. So there's that. You can also mess with, hey, what if I flip these around, right? Inductor, capacitor, it's gonna flip around, get a band stop. But there's also different ways you can terminate these filters, not just by terminate, I don't mean with the resistors, but what things you put here and here, and you can switch the order. For example, if you just remove this inductor and have this go straight there, what does this look like now? You can mess around all that in that little app. And we're gonna be mainly sticking to either Trebuchet or Butterworth filters. The app will spit out the Bodie plots for you. So all you have to do at that point, it's really nice, you can spit out the Bodie plot, you can take out the LT-Spice file from it and copy it into your LT-Spice, and it'll make it for you. So literally the assignment, you'll have your mixer. It'll be like, okay, what's your conversion loss, your isolation, your LO isolation? Make the filter, put it on there, which you can just copy paste, and now look at it. It's pretty great. And those are filters. Beyond this, we're not gonna talk about filters again until some R&D lecture in spring. But they're pretty useful for that. Yeah, we don't want to go past fifth order just because it gets very tedious. And hand winding all these inductors to be very specific values, it's going to spit out like 473 nanohenries or something like that. Like, okay, I can't really make 473, at least make it and have always be 473, because you're hand winding them, right? So that's something that we have some remedies for, we're going to talk about. But for the time being, that's the last half of the assignment. Any questions on that? Okay. I may talk about active filters relatively soon. I think you'd enjoy that. Yeah. With working op amps this time. With working op amps. Yeah. That's huge. Yeah. So that'll be fun. Any questions on this? The main part of the assignment is the mixer itself. So any questions on that? None at all. Okay. I believe that should be it. Some announcements. Well, Brenda will come back. That's good. This Sunday, oscillator work session. We're going to be making the oscillators and maybe some miscellaneous boards like just the antenna board or like some power boards, basic soldering stuff. It's not neat for you to go. I mean, I'd like you to, but they're not very technical. It's just assembling things. The lectures and the modules are the most like technical part. They can show them, help assemble, right? But no worries. Weekend after next, I'm planning on having us assemble the mixers at the work session. So ideally, you finish the assignment, so at least you know what the jive mixer looks like, so you can solder it. You don't have to finish it, but it'll give you some notion of, hey, what does it mixer look like? What do we expect? Blah, blah, blah. Because it's hard for you to solder something when you don't even know what the circuit looks like. So some exposure to that would be good. It's a bit of a tight schedule. I know, like 1 week turnaround. The next lecture, I'm planning on having a bit more of a break. But the mixers and the oscillators are like, we get that out of the way, and then it's like, we make filters, we make like miscellaneous stuff. Amplifiers can get scared anyway, so it's like, it's a bit tight for like the next 2 weeks. And it's kind of right in the middle of midterm season, so it's like not the biggest deal. But you can do it great. I think it's one of the easiest assignments so far, so.
Just like timelines. Is it okay if like let's say I can book for like 2 hours, like maybe 3 hours, but I should probably do a lot of studying this weekend.
Yeah.
So
I mean, I don't care, yeah. I'd rather you study than show up.
But I want to help out. Also, like,
Yeah.
I should perfect my essays. So.
This is true. That's something is a useful skill. can show up, great. I mean, we're gonna make.
I'll be able to pull up, I don't,
Yeah.
when I'm there, I'll let you know.
Okay.
Cause I'm gonna be real, like,
Next week's busy.
yeah, like,
Yeah.
it's 150B and 101B. And,
Yeah.
I'm not too concerned about 101B, but like lately some of the others just be popping up with random questions.
Yeah.
I have no idea.
I mean, just to put into perspective, it's like, we're gonna make 4 oscillators, 2 4,
Yeah.
and then, 222. And you saw how quick the oscillators are. They're not that quick in the capstone, but yeah. Yeah.
I mean, they're alright.
Yeah, it won't be too bad. If you can show up, great, if not, no worries. To recap what I said. It's a bit of a tight turnaround, like, to make sure times, I'm like, yeah,